Imagine witnessing a breathtaking spectacle that most people on Earth will never see. While many of us are familiar with the rumble of thunder and the flash of lightning during storms, astronauts aboard the International Space Station, ISS, have the unique opportunity to observe stunning electric displays that occur high above the planet, soaring up to 55 miles in the atmosphere. These vibrant bursts of color, which include blue jets, red sprites, violet halos, and ultraviolet rings, are collectively referred to as Transient Luminous Events, or TLEs. For many years, these phenomena remained largely unstudied, existing only in the stories shared by pilots and the occasional fortunate photograph. However, the ISS has revolutionized our understanding of these events by providing an unobstructed vantage point above the storms. Equipped with specialized cameras and sensors that capture every fleeting moment of these extraordinary displays, researchers are gradually uncovering the significant impact these hidden atmospheric events can have. They can disrupt radio communications, pose risks to aircraft safety, and even alter the chemical composition of the upper atmosphere. A storm laboratory in space. At the heart of this groundbreaking research is the Atmosphere Space Interactions Monitor, ASIM, a sophisticated instrument developed by the European Space Agency. Since its installation on the ISS in 2018, ASIM has been diligently observing Earth, capturing flashes that are smaller than a fingernail and shorter than a heartbeat. The high-speed cameras and photometers on board have exceeded scientists' expectations, revealing that certain lightning-like discharges at the tops of thunderclouds can inject electromagnetic energy into the ionosphere, creating vast rings of ultraviolet light known as ELVs. These rings can enhance the ionospheric charge over hundreds of miles, potentially interfering with long-distance radio signals. ASIM has also documented extremely brief corona discharges, events so fleeting that ground-based instruments often fail to detect them. By analyzing the timing and characteristics of these coronas, researchers are beginning to piece together how the upper regions of clouds set the stage for full-scale lightning strikes. The enigmatic red sprites. Among the most intriguing phenomena are the so-called red sprites, which appear randomly in the mesosphere, resembling upside-down jellyfish for a mere 10 milliseconds. Meanwhile, blue jets shoot upward from the tops of clouds toward the stratosphere, with a silent urgency that is both eerie and fascinating. These events occur so rapidly and at such high altitudes that capturing their details has historically been a challenge. However, ASIM is now able to observe them from orbit. One particular study utilized ASIM's footage alongside ground instruments to accurately determine the altitude of a single blue jet, confirming that these upward bolts indeed extend beyond the familiar weather layer. This data is crucial for refining storm charging models, which help inform aviation safety guidelines regarding the presence of hazardous electrical fields. Capturing storms from space. The ISS's cupola, a 7-windowed observation dome often featured in astronaut selfies, has become an essential tool for scientific research. Through the ESA's Thor-Davis experiment, crew members on the ISS have attached a cutting-edge camera behind the glass to capture distant storms at an astonishing rate of up to 100,000 frames per second. The resulting slow-motion footage reveals intricate electrical filaments, forming in ways that textbooks have yet to predict. By documenting the rapid branching of lightning in vivid detail, Thor-Davis aids scientists in validating laboratory plasma tests against real-world occurrences. More importantly, this footage could eventually enhance the algorithms used to alert power grid operators when severe lightning threatens transmission lines. Unveiling the hidden drama of lightning. The drama of lightning extends beyond what is visible to the naked eye. Some lightning strikes trigger terrestrial gamma-ray flashes, which are pulses of radiation powerful enough to expose an airliner to a brief surge equivalent to a chest X-ray. To map these invisible dangers, the Japan Aerospace Exploration Agency, in collaboration with university partners, launched Light 1 from the ISS. This CubeSat, no larger than a loaf of bread, is equipped with detectors specifically designed to capture high-energy photons. As Light 1 records flashes over equatorial storm systems, researchers aim to synchronize its timestamps with global lightning networks on the ground. Over time, this will help create a three-dimensional atlas detailing where gamma-ray flashes occur most frequently. The impact of storms on communication. At first glance, one might dismiss a Sprite or an Elvis ring as mere meteorological curiosities, akin to a high-altitude version of the aurora. However, these flashes erupt in the same charged layers that carry radio waves and transmit signals to submarines. Disruptions in these layers can lead to sudden communication failures. For airlines, understanding the timing and locations of blue jets or gamma-ray flashes adds an essential layer of safety planning, particularly for polar or equatorial flight routes. Scientists are also concerned about the implications for climate. TLEs and corona discharges can shuffle nitrogen oxides and other chemicals between different layers of the atmosphere, affecting ozone chemistry and the radiative balance. Incorporating this vertical mixing into climate models can enhance predictions regarding future warming. Advancements in lightning tracking, with the ISS expected to remain operational throughout the decade. ASIM and its successors will continue to build a comprehensive library of previously invisible storm events. Engineers are envisioning next-generation detectors that will automatically trigger, record at faster rates, and cover a broader spectrum, from radio waves to hard X-rays. CubeSats like Light 1 could multiply into a fleet, providing real-time alerts to weather agencies and satellite operators whenever a gamma flash or mega sprite occurs. Ultimately, the ISS demonstrates that to truly understand Earth's weather, one must sometimes look down from above. Each orbit adds more frames to the hidden movie reel of lightning, bringing us closer to predicting and potentially mitigating the electrical surprises that storms unleash into the upper atmosphere. Did you find this information enlightening? If so, consider subscribing to our newsletter for more engaging articles, exclusive content, and the latest updates. Check out EarthSnap, a free app created by Eric Rawls and Earth.com, for more fascinating insights into our planet.